So the final thing in this unit is to discuss R squared, which is a measure of how well a regression is doing. Now the formal definition of R squared is the following, right? R squared is the percentage of variability in the response variable that is explained by the regression. But I understand that that has no so much there that we have to unpack that slowly, and that probably means nothing to you at this point. But it seems obvious that R squared is the percentage of something that is explained by the regression. Clearly we want to explain a lot, and so we would like, at the very least, we can tell from right away that R squared ought to be a big number. It is going to be a percentage, so 100% would be the ideal to which we go towards, we want to see, although in reality R squareds are never really that big, but the closer to 100% the better. So let's set something up here. What I want to do is imagine that we are in a room and on campus, and a random male, could be any UD student, any male UD student, is going to be coming through the door, and what we'd like to do is guess his height. Now, by the way, I'm picking on the men simply because I don't want to deal with, men and women together, because of the bimodal nature of heights of the two sexes, but and I chose to focus on the men, just kind of arbitrarily. So we want to guess the height of the men coming through the door, but it would be better if we had some data, because we might try to guess, I don't know, 5'10" or something like that, but really what we ought to do is look at what men at UD are like, because that would be the most helpful kind of information. So what I've got here is actually a sample of UD men, a histogram of their heights. Okay, and obviously the reason you said 5'10", I'm assuming, right, is that you would think, well, I'll pick something in the middle, right? If I have to guess their height, I'm not going to pick 8 feet tall or 4 feet tall, because those are too extreme. I want to go something in the middle, because that'll make it most likely that I'm close to the right height. And you can see that this data kind of reflects that, because what we've got, right, is the mode there, which is around 68 inches, which happens to be, 5'8", because 65 feet tall is 60 inches exactly, and 68 would be 8 inches taller than that. So perhaps that mode is kind of pointing us towards 68, 69 inches tall rather than 70 inches. But something around the middle. And again, it would be silly because to guess out here or guess out here 60 inches or 76 inches, because there aren't many men out there, and I'm likely to be far away, where if I guess at something in the middle, then I'm going to be close to many of them, right? Many of those, the possible men that might walk through that door. There's only going to be one that walks through the door, but I'm thinking them as the group, one being selected. So, and that's exactly the right thing you should be thinking. Makes a lot of sense. But in some ways, what I'm more interested in this part of the presentation is trying to get a handle on how bad it's going to be. How far am I going to be? Okay, I know I'm going to guess at something in the middle. My guess will be something in the middle, but how bad is that guess? In the sense that how far, in general, the person will be from that middle guess. The problem, the issue here is that the variability of their heights is what really causes the biggest problem for my guessing, right? That my variation If it's high, it's going to make it difficult. If it's low, it's going to make it easy. So to demonstrate that, let's assume I'm going to sort of say, well, let's think of three different scenarios of heights a minute UD. So, for example, here is a supposed, fake distribution of heights. You notice that the middle is right around 68, like I had said before, right? 68 seems like a reasonable guess, 67, 68. And what I'm saying is it's going to be an easy scenario because really there's no men anywhere farther than 65 and no men greater than 70. So guessing at 67 and a half is going to get me within a couple inches of everybody. Okay, so this is going to be easy to guess. Where I'm going to consider my real data. It might be, I would say, it's going to be harder, but I'm going to say it's going to be medium because I'll make an even harder scenario because I'll guess here, and while I'll get some that'll be within a couple inches of each other, a couple inches of my guess, there will be the chance that I'm way off, right on either side. There is this possibility that these men that are extremely tall or extremely short show up, right? Where in the previous one there was no chance. There's just no men that way in that scenario. And what about an even harder scenario? Well, if there's even more variability, and that's the key here, right? So I've got lots of men way out there, and my middle is still the same place. That's the point of this graph, is everything's the same as far as the guess is given, but the higher variation here means that I'm likely to be far away, right? And so I'm going to be far from what the guess that I give, even though it's the same in all three cases. The guess that I give in this third one is going to be more likely to be far wrong than in the first one. Okay? So variation is the enemy, right? All right, this is bad. Okay, so to summarize this, we're going to say, okay, well, the logical thing to do is guess the mean of the data, because that's the middle. And a measure of how bad you'll do is the standard deviation, because that's a measure of variation. If the standard deviation is big, you're going to do badly. If the standard deviation is small, then you'll probably do all right, right? So again, this is this notion that variation is the enemy. Now, all of that being said, we haven't brought in regression, so let's do that. Let's assume that before I have to make my guess, it is going to be revealed the shoe size of the fellow who's going to walk through the door. I'm going to find that out, and I can use that information if I want to. Should I use that information? And the answer is absolutely. Look at the scatter plot of the shoe sizes and the heights of the men that I showed in the previous histogram. Okay, and you notice that when I have a size 8 shoe or something like that, I should be guessing at heights down there in the low 60s. But if I find out that it's a person with size 14 shoes, that should be my guess ought to be up in the 75 range, right? And in fact, the interesting thing is that I should really be guessing at what, using the regression line, right? So here's the equation for the regression line that I computed for this scatter plot. And if somebody came in with size 10 shoes, well, then I ought to guess using the regression line, say coming up here, coming over, and whatever that regression line tells me, because that's in some sense the middle of the size 10 shoes. Okay. And in fact, when I get, so let's say instead of size 10, 10 and a half, I'm going to guess using that regression that the person will walk in the door at 69.5. But again, I want to know how bad our guess is. And this mysterious yellow blob is actually supposed to highlight that area of the graph, that 10 and a half shoes. You can see that, yeah, I'll guess at 69.5, which is in the middle of those points. But it might be, it might be as tall. There are some guys with 10.5 shoes that are up there, and 73, it looks like, inches, and some that are down in the 70, 68 range, right? So even though my guess is 69.5, there's still the possibility that I won't get it exactly. The guy will walk in and be a little different. So, but you notice here, I'm using the variation just of those, those those heights around the regression line, right? So I don't really want to use the standard deviation of the whole shooting match, the standard deviation I had before of all the heights. What I'd rather do is use the standard deviation of the residuals, right? Because when I look at this graph and I look at those 6 points here, right, the residuals tell me how far above or below that regression line I might be. And it's is common to find that actually the standard deviation, so the variation around that line is about the same all the way across. Okay, so I'll use the standard deviation, the residuals, as my measure of how bad I'm going to do, because that's what's really important, since the line is going to take care of some of the the changing my guess to maybe be closer to the group of guys based on their shoe size. Okay, so what I'm going to compute is the standard deviation of the residuals, and we have the same kinds of three scenarios. Right, in a situation like this, and this is just hypothesized data, simulated data, everything is really close, right? All the dots are fairly close to the line. So if I guessed at the line, right, so 10.5, I guess, 69.5, and but I'd be within a couple inches, because that's where everybody is, right? Everybody's within a couple inches of these lines. So this is going to be really easy. I'm going to probably get the right, close to the right answer. Oops, sorry. My medium case is, again, the data I was using, where, well, I'll guess it's 69.5, but there is a pretty good chance I'm going to be far away, a couple inches away, right? But, not that bad. But it could be hard, it could be worse. Like this, I'd say 10.5. Oh my gosh, it's still the same 69.5 that I should guess, but it's possible that that person could be as tall as way up here, or as short as way down here. And so I'm going to have lots of messy, far guesses, because the variation of the residuals is so high. So how do we use this idea? And the answer is we compute this quantity r squared, and it turns out that we don't use the standard deviations, but instead the squared standard deviations. And so here is a ratio, a division. The standard deviation of the residuals is in the numerator. The standard deviation of the original data, the original height data, is in the denominator, and I've squared both of them. So the bottom, think about what that means, is I was trying to guess at their height without using the regression. So it's just sort of all the variation that's in the heights, no matter what shoe size. I don't even know shoe sizes in that case, right? Where the standard deviation, the residuals, are in some sense the standard deviation, the variation that's there after I've sort of adjusted each group of guys by their shoe size, right? So I make a slightly different guess for each shoe size that helps me get closer to that group of shoe size guys. And so that's the variation that's left over in the regression. And there's still some variation, right? I mean, 10.5 shoe size does not tell me everything about that person's height. I'm not going to guess it 100%. So there's still variation there. Now, this is interpreted in the following way. If this is close to 0, what does that mean? It means the numerator is pretty small compared to the denominator. That is, the numerator is pretty tiny. So with the variation, what is that saying is that there isn't much variability left in the residuals. So that means actually things are good. Okay. All right. Because that standard deviation of residuals is small. Um, there's not much left over. Whereas if it's big, oops, like close to 1, and in fact it can't get any bigger than 1 because the residuals can never be bigger, have standard deviation bigger than the original data, that means we're not doing much better. That is, these two quantities are about the same. So the original variation and the variation after I have a regression are about the same. So my guess is, I tell you the shoe size, well, you're just as likely to be far away as you were before you told me the shoe size. So actually, the regression is not helping much when this is large. That's opposite of what I wanted in some ways, because remember we said that R squared was supposed to be large. We want to look for a large R squared. Here it's kind of saying that a small R squared would be the better in the better regression, the smaller the R squared this quantity is. So what we'll do is we'll actually take this same quantity and subtract it from 1. All that will do is invert it all. So R squared is just 1 minus this ratio of standard deviations. The nice thing about that is when this is close to 1, I have a really good, right? Because what does that mean? It means I'm taking 1 minus something small. Oh, that means this is close to 0. Okay, so that's good. Where when this is close to 0, I'm subtracting from 1 something that's close to 1, right? Because 1 minus something, 0.99 is pretty close to 0. That means I'm not doing very well because the variation of the residuals is still large. So the final analysis is this is helpful. In fact, it's particularly helpful because I can interpret it R squared, remember, as a percentage. I said this at the very beginning. So but it measures the regression success. An R squared of 78% is a better regression than one with an R squared of 25% because I am explaining more variability. This is not the only thing I should be considering when selecting a regression model, but it is an important one, so we'll keep it. So finally, I want to finish with a example. So the height versus shoe size has a R squared of 0.4958. And of course, by the way, I'm not computing that by hand. I'm using the computer. And what I can interpret that as, right, because it turns out to be a percentage, is that's a 49% or maybe even 50% of the variation in height is explained by the regression with shoe size. So think of the height. I had all that variation. Some guys were tall, some guys were short, but I didn't know why, and so I just had to guess at the middle. Here, I now can make a more subtle guess depending on shoe size, and my variation is decreased because when I have a size 12 or a size 10.5, I don't have to worry about the really tall guys and the really short guys. I just worry about that smaller group of individuals that are around that shoe size.